All right. So good morning. My name is Zainul Turbiwala, and this is collaborative work with the neuroscience department at UCLA and the circuits group in the electrical engineering department at UCLA. I work with Dr. Srivastava at the Network and Embedded Systems Lab, affectionately called NESSL. And this work is about acquiring neural action potentials, or what are termed neural spikes, and how to do it in a low power way using signal processing techniques from compressed sensing. So I'm going to go through a little bit of introduction to compressed sensing for those of you who don't know. So what's the aim? So this is what they currently use. This is a picture from in a magazine article. But this is this kind of system that they use, which is a huge test cart, and this person is smiling, but this person is not. What we'd like to do is basically this is the electrode array from the University of Utah, and they've been pioneering a lot of this work. And what we want to do is combine with our circuits expertise, put all the electronics behind this electrode array essentially. And I picked something up from Dr. Sanders' talk last night, and he talked about how the exam room should come to the patient, and I think we should go to the extent of putting the exam room in the patient. So this is what an implanted electrode going right into the deep part of the brain, and in this case the hippocampus, looks like. And this is the signal that comes out from this sort of electrode. And it's a fairly noisy signal. There's a lot of information here, but to get to this information, we need to do a fair bit of processing. So the first thing that's done is a bandpass filter that gets rid of most of the DC offset, and what is called the local field potential, which is the low frequency side, which is what you pick up when you do a scalp electrode. So this is deep implanted electrode. So this is really from the innards. And the neuroscience department is especially interested because they're looking at epilepsy patients and trying to do deep brain stimulation for these patients. So what they're looking for is essentially the spike signatures. And after you do this sort of filtering, you see there's like spiky behavior. This is only about 350 milliseconds worth of data, and we have a lot of data. We'll talk about that a little bit later. And what is typically done is from this data, there's multiple different algorithms for detecting spikes. The one that we use is called NEO, or the nonlinear energy operator. And that essentially picks out the spikes from the signal. And the key thing is that it's the spikes that's important and not the noise. And what's typically done is that you acquire all of the signal, you send out all of the signal over the wireless channel, and that's completely unnecessary. The other thing to note is that these spikes are actually from multiple neurons, because the electrodes pick up signals from a lot of them in that vicinity. And if you take all these spike signals and you align them at some point, and in this case it's aligned at the highest slope, you get a bunch of different waveforms that look like a big mess. And in this case, this is about 1,000 spikes laid one on top of the other. And after this alignment operation, what's typically done is you do a sorting operation. And what sorting does is it picks up the morphology or the waveform pattern from each neuron and tries to assign each pattern to a specific neuron. And what's known is that each neuron has a distinct morphology, and using that, exploiting that property, you can sort out what may be noise that the detection algorithm picked up as a potential spike. And so what neuroscientists are interested in are two things. One is the spike rate, as in when the spikes occur in time, and they care about the morphology in the sense of which neuron is active. So what sort of the process looks like is you have an electrode that's implanted somewhere in the brain, and you have an amplification slash and digitization process. You filter it, you do detect and align, and you transmit that over a radio channel. And on the other end, you receive that signal, you perform spike sorting, and do whatever analysis you need to after that. So that's what people do today. And what we're proposing is essentially adding a few blocks in the middle, which is one, we add a compressed sensing block on the transmitter side, and on the receiver side, we add a compressed sensing recovery block, and this block, which we'll talk about a little bit later. So for compressed sensing to work, we need to have two things. One, that we are able to do some sort of measurement acquisition that distributes the energy from the spike into a few measurements. And the key thing is that the spikes should be compressible in some domain. And in this case, what we found was that the spikes are compressible in the wavelet domain. And the other thing that we are going to exploit in this work is that spikes from the same neuron are similar in morphology. That's how spike sorting works. And so we should be able to use that similarity in some way in order to reduce further the transmission rates required for getting all the analysis done. So if you look at this is just one spike, and it looks doesn't look too much like a spike, but it's because it's just stretched out. And if you look at that spike in the DWT domain, the discrete wavelet transform, we see that only a few of these coefficients are really high coefficients. All the rest are pretty much zeros. And this is one of the key properties that you need for compressed sensing to work, in that the signal, though in the time domain has a fairly distinct signature, in the DWT domain there's only a few places where there's energy there. And essentially every lossy compression system works by taking these significant coefficients and throwing out the rest. So if we, so this is only for one spike, but if we look across many different spikes, and this is for 1,000 spikes, this is what the number of significant coefficients in terms of the 99% energy is contained within about 11 or so coefficients, 11 or 12 coefficients across time. So across all the spikes, we see that they are all compressible in time. And this is sort of a histogram of the same thing, and it's got about 11.48 mean, and a fairly like about 3 or 4 coefficients in standard deviation. And so in terms of compressed sensing, what we need is this, what is called the sparsity inducing transform. In this case, it's the DWT. So let's say that we have the signal and we've already digitized it. So this is a discrete time domain. And so we'll call that signal X. And let's say it's of size N. And when you apply the DWT, let's call that the DWT is a linear operator. We can model that as a matrix. And what you get is these sparse coefficients, and we can call this Z, which is some psi times X. And what compressed sensing now involves is, so you've got this X, and you want to send something over to the receiver that can give you back this representation at as low a transmission rate as possible. And so what is done is that a pseudo-random matrix is generated, and that's called the sampling matrix phi. And that is a fat matrix in the sense that it has more columns than rows. And this matrix is multiplied, you could say, to the signal that we care about, and you get fewer measurements, since it's a fat matrix, you get just m times, and they look fairly random. They don't look like the signal. They don't look like the sparse version at all. And just we'll call this y, which is just 5 times x. And what's done is that you send m over, okay? And so your compression ratio is n is to m, essentially, all right? And so what you hope is that from this y and knowledge of phi and knowledge of psi, you'll be able to recover your signal back. And so this is like a simulated result from actual data. And so you've got this y, and you put it through a nasty looking optimization solver, and the key thing here is that there is some component here which is an L1 norm of z, which was your sparse domain, and there is some penalty based on the 2 norm of the error. And there is significance due to this, because that's where the noise robustness comes from in this system. So what you get at the end of the day is that from these m measurements, and these were, I believe, 32 measurements for 64 samples, and the red line is what you get from using these 32 to generate the 64 back again. And so you give your y to a solver, you give your knowledge of phi to the solver, you know psi is your DWT, and it gives you back a z hat, which you put it back with psi, and you get your waveform back in the time domain. So that's generally the operation that is done for those who don't know compressed sensing. So that's what we started with first, and we said, okay, let's try putting that compressed sensing block into the transmission system, and then we do a recovery over here, and how does that perform? So this is the first result we got from looking at different number of measurements per spike. So we've already detected the spikes, we've aligned the spikes, so we have spikes in windows, and for each spike we use between 4 and 48 measurements. And this is what I showed you here is called the L1 minimization, or what is also known as the basis pursuit algorithm. And so that's the conventional basis pursuit algorithm, and this is sort of what it looks like in terms of the performance in SNR or SNDR, which is with distortion. And what we saw is, like, you need about 35 measurements from that 64 sample signal for 20 dB SNR, which is sort of considered by the neuroscientists that, okay, that's acceptable to us. Okay, this is sort of a gray area, because a lot of neuroscientists were, no, we want everything. And I don't know what everything means to them, but they say that we want the raw signal. But when we show them a 20 dB SNR signal, they can't make out the difference anyway. So we think that a 20 dB is a good line to draw. And so this signal, result is across around 500,000 spikes that were taken from 3 different data sets spanning a few hours from the deep brain electrodes. And what this resulted in is sort of a 1.3, 1.4. So it was fine, but it was not great. The 18x compression comes directly because we are throwing out all the noise between the spikes. So that's the 18x that comes from that, and the 26x comes after you do this sort of compression. So we said, all right, fine. So spikes are compressible in the wavelet domain. We use that. Now let's try to use the similarity. And so when we looked at 2 different spikes, even from 2 different groups after they are sorted, what we saw in the wavelet domain was that a lot of them, though they were different values in the wavelet domain, the black dots represent where the indices in the wavelet domain matched between the 2 spikes in terms of their positions, not in terms of their values. And that's also interesting and also something that we can exploit from a compressive